This video is part 2 in a series about using simple continued fractions as part of the process to generate Pythagorean triples. We'll write a quick problem statement and outline the process, and then work an example. Let's get started. What we want to do is use simple continued fractions while generating Pythagorean triples. Here's the process. First, calculate convergence for any simple continued fraction. Any simple continued fraction. The simple continued fraction can be finite, or you can find some of the first convergence for one that is infinite. Then, you can use the values of p and q, the numerators and denominators, of the convergence, and substitute them for m and n in Euclid's formula. The result will be a Pythagorean triple. You can do this for any convergent except the first one, when k equals 0. Sometimes you can use the first one, but we'll mention reasons in this video to not bother using it. Here is Euclid's formula, which we discussed in this other video. If we have any pair of integers, which we denote m and n, then we can generate a Pythagorean triple from a equals m squared minus n squared, b equals 2 times m times n, and c equals m squared plus n squared. We're going to use p and q for the values of m and n. So, if p is greater than q, we use p as m and q as n. But if p is less than q, it's the other way around. We use q as m and p as n. In any case, the result will be a Pythagorean triple. Here's something else about Euclid's formula. If m and n are coprime, and exactly one of them is even, the triple is primitive. If we apply this in our process, in which we're using convergence, if exactly one of p and q is odd, the Pythagorean triple will be primitive. This is because p and q are always coprime. Now let's think about what's going on. The role of simple continued fractions is simply generating values of two integers that we can use in Euclid's formula. The convergents provide us pairs of integers, denoted p and q in the convergent, that we can use as m and n in Euclid's formula. Here's a reason to not use the convergent when k equals 0. The value of p can be less than or equal to 0, so this condition, this one here, might not even be satisfied, so in this case the p-q pair cannot even be used as m and n. Also, when k equals 0, p can equal 1. And q always equals 1 when k equals 0, so once again this condition isn't satisfied, and the pq pair can't be used as m and n. To put this another way though, you can use the first pq pair when k equals 0, whenever p is greater than or equal to 2. I really don't want to belabor this point about the first convergent though. It's best to just not use it. Let's look at an example. We can use any simple continued fraction. We'll use the 1 for the square root of 2, which is 1, 2, with the 2 repeating. Remember the process. The first step is to calculate convergence. In another video, we saw how to calculate convergence using a spreadsheet, and we'll use that spreadsheet now. Here it is. We have a row for the subscript k, and another row for a, the values of the simple continued fraction, and rows for p and q, the numerators and denominators of the convergence. The spreadsheet already has equations for p and q. Here are a few cells. You can see they have equations. The current values they calculate are 1s and 0s, but that's because we don't have values for a filled in yet. When we fill them in, p and q will update automatically. The 1 goes here, in the column for k equals 0, and then the repeating 2s. We'll fill in the first 2 of them, and then we can grab the handle and pull it over. It fills in a equals 2 for each of those cells, and look, now the rows for p and q have numerators and denominators of the convergence. Let's take a quick look at the process again. Our next step is to use the pairs of p and q for m and n in Euclid's formula. Here's Euclid's formula again. Let's bring back our spreadsheet. Notice that in this case we have to skip the first convergent because p equals q. This violates the condition for using them as m and n in Euclid's formula. After that though, the convergents meet the condition. They work just fine and we can calculate a, b, and c. In each convergent p is greater than q, so we'll use p for m and q for n. We'll keep using the spreadsheet and add the equations. For m, we use p, and when k equals 1, p is in cell E3. For n, we use q. When k equals 1, q is in E4. Make sure you use the addresses like this and not the actual values. A equals m squared minus n squared, so that's E3 squared minus E4 squared. B equals 2 times m times n, that's 2 times E3 times E4. And c equals m squared plus n squared. That's E3 squared plus E4 squared. There, we have one triple. To get the rest, we can just grab the handle and pull it to the right. Now the rest of the columns have a Pythagorean triple. Let's see which of these triples are primitive. Remember the conditions. If m and n are coprime and exactly one of them is odd, the Pythagorean triple will be primitive. What's nice about using p and q for the values of m and n is p and q will always be coprime. Therefore, if exactly one of them is odd, the triple is primitive. When we look at p and q, we can see that each value of p is odd, and q alternates between being even and odd. Therefore, when q is even, exactly one of p and q is odd. We're using p and q for m and n, so exactly one of m and n is odd, and the triple will be primitive. q is even in each of these columns. This pattern will continue for as many convergents of the square root of 2 as you care to calculate. You can put the values for any simple continued fraction in the row for a, and you'll have Pythagorean triples in these rows. In this video, we outlined the process for using simple continued fractions as part of the process of generating Pythagorean triples, and we worked an example using a spreadsheet. That's all for now.